Good evening, and welcome to the Scientific Adventures of Beardman. Today we're going to take a look at it's going to be the first day we get to take a look at current, about how electrons flow through something like a piece of metal, like a wire. So in order to do that, we have to discuss three variables that we'll need to understand and be able to measure in order to talk about a current. The first one is current. Current has the symbol of a capital I, and it's measured in units of amperes. Okay, so what is current? Well, current is the amount of charge that flows past a point each second. So imagine you're a little imaginary gatekeeper, and you're clicking your counter every time an electron goes by you. You're sitting inside of a wire, an electron goes by, you click. Another electron goes by, you click. Okay? Well, that would give you could then count up the number of electrons that went by you each second. Now, we don't measure it in terms of electrons, like we saw in the last video. We have such a large number of electrons, we have another unit for that we call the coulomb. Okay? So an ampere is the same thing as saying coulombs per second. So 1 ampere means 1 coulomb of charge, 1 coulomb of electrons flowed by each second. You could also, of course, say if there are 3 coulombs of charge going by each second, that would be 3 amperes. Or for short, we often say 3 amps. Some people talk about that as though it's an equation. Current equals charge divided by time. Okay, but in terms of the unit, if you understand that an ampere is telling you how many coulombs go by each second, it just kind of makes sense. If I say there's a current of 8 amperes or 8 amps, and I ask you how much charge goes by in 2 seconds, well, if 8 coulombs are going by each second, then 16 coulombs will go by in 2 seconds. You're welcome to go ahead and use the equation, I equals Q over T. Lowercase q is the symbol we use for charge. It's measured in coulombs, which is a capital C. And T stands for time. The second variable that we'll need to talk about is voltage. Okay? Voltage is also known as potential difference. The symbol for it is capital V, and the units for it are volts, or lowercase v, although sometimes you'll see units as capital V as well. The definition is the difference in potential energy, specifically electrical potential energy, between 2 points. So imagine we've got an electric field here, and we take a charge and we move it through that field. We're giving it potential energy. Okay? Just like if we take a book and we lift it through a gravitational field, that would give the book gravitational potential energy. In this case, if we take an electron or any charge and drag it through an electric field, we're giving it potential energy. So voltage describes how much potential energy it has per charge. So it's describing how much energy 1 coulomb of charge has at one place versus another. Okay, so if the difference between here and here is 4 volts, that means each coulomb of charge has 4 joules more energy over here. Well, where do we hear that most often? With batteries, right? And that's where you hear about voltage. AAA battery has 1.25 volts, or a 9-volt battery has 9 volts. What that's saying is that each coulomb of charge that moves from one to the other will lose, will lose 9 joules of energy. Every coulomb will lose 9 joules, and that 9 joules will transfer into some other kind of energy, be it thermal or light or mechanical if it's running some sort of a motor. Okay, so every volt tells us how many joules each coulomb of charge will lose as it goes however it gets to the other place in the electric field. The third variable that we have is resistance. Okay, resistance is kind of like it sounds. It's the opposition to the flow of electric charge. Resistance has a capital R, and it's measured in units called ohms, which are abbreviated with the Greek letter omega, which you can see here looks like a horseshoe. The definition, as I said, is the resistance, the opposition to the flow of electric charge. It is a property of a material. So I could hold something up like my key. Okay, my key has a certain amount of resistance to electric flow. If I hooked this up to some sort of battery and tried to push charge through it, well, this material with this thickness and this length will have a certain amount of resistance. We're going to look at that more later, but for now, the basic idea is the material itself can resist electrons flowing through it. If it's a metal, well, metals have a pretty low resistance because the way metallic bonds work, they all share electrons. So those electrons can share all the way through it pretty easily with a fairly small amount of resistance. If you have something else like wood, the electrons are pretty much stuck on the molecule that they're covalently bonding to the other atoms with. And so they can't really flow through very easily, so it takes a lot of pushing to rip them off the atom and carry them to the next molecule. So therefore wood would have a high resistance. Another way we could decrease the resistance is to make the material shorter. If we're only going from here to here, well, it's going to take less energy to get the electrons through there. If we have a really long thing, well, then all those electrons have to shift at once, kind of, and there's more resistance in that case. And if you have a skinnier wire, well, then all the electrons have to go through, have less options of how to get from here to here. They have to go through that skinny thing. If you have a big wide tube, it's like in plumbing. If you have a big wide tube, there's an easier flow. There's less resistance. The electrons can move in this part or this part or this part, and so it's easier for them to get through. We'll revisit that when we look at resistors in parallel and in series in the next video or in a future video. Now we have to look at how these things all tie together. The equation that ties these three variables together is called Ohm's law. Okay, and Ohm's law, like I said, ties these things together. And so the first thing to notice that hopefully was obvious when I said it is that voltage, how much energy difference there is between the two sides, you can kind of think of it as the push through the wires, okay, or through the circuit. The voltage, if we increase the voltage, if we increase the push, well, then we're going to increase the flow of charge through it. Okay, so voltage and current are directly proportional. As you push harder, you get more flow of charge. Okay, they're directly proportional. Then if we look at resistance, resistance opposes the flow. Well, if we have more resistance, if we have a bigger force opposing the force is not the right term, but it's the idea, a bigger resistance opposing the flow of charge, well, then we're going to have less current. There's going to be less flow of charge. Okay, so resistance and current are inversely proportional. So we can see the voltage increases the current, the resistance lowers the current, and so we get an equation I equals V over R. Okay, you will often see this rearranged to be V equals I times R, but that's just a little bit of algebra. I prefer I equals V over R in terms of understanding the equation, because current is kind of what we're getting out of this thing. Then if we look at how hard we're pushing and with the material that the electrons have to flow through, then we can figure out what the current is. Okay, so conceptually, I equals V over R is a great way to look at it. And that's Ohm's law. Hope you enjoyed learning here on the scientific adventures of Beardman. We'll see you next time. Get all charged up. Alrighty. Bye-bye.